H of the this spin chain or this lattice is given by really the tensor product of the individual Hilbert space sitting at each lattice site. Okay, so I'll write down what this actually means, give this example. So, and each of those operator, whatever it is, like the spins or momentum position, or generally denoted as x alpha n, is really an operator which acts trivially at all other sites except at the n site. Still trivially. Only act non-trivially at the n site. Okay? So it really only picks up, acts on this particular spin, or acts on a particular the Hilbert space Hn. Only. So of course, this is only true for that ultra-local case. Okay. So as a simple illustration, so how many of you seen tensor products? You have, right? So I'll just write it down for those of you who haven't. So for example, for given two matrices A with I don't know 2 by 2, let's say A1, A2, A21, A22, okay, and B similarly with the labels. Then A tensor B is given by A1, B, A12, B, A21, B, A22, B. So B will be 2 by 2 matrices sitting here. So altogether, this would be a 4 by 4 matrices. Or generally, if you have two n by n matrices, tensor with the n by n matrices, so we would get n squared times n squared dimension matrices or matrix can represent that, and the same with the vector space. Sorry, they are tensor to each other. So here, because I'll be using this tensor notation quite heavily in the subsequent discussion. I'm going to get this out of the way. Okay, so for example, A some vector A1, A2, B1, B2. So all of them are complex. So A tensor B really means A1, B, A2, B. Or we can write it out. There will be 4 components: A1, B1, A1, B2, A2, B1, A2, A2. Good. So basically, if you have this guy acting on this guy, so we have a 4 by 4 matrix multiplied by 4 column, well, 4 entries column vectors. So generally, if we are looking at, I don't know, yeah, so for most of the case, we will be looking at really at each site. So we'll be looking at really spin half case. So SL2. So each of those ones are really just a 2 by 2 matrix, and this will be a 2-dimensional. Each of Hn will be a 2-dimensional complex vector space. Okay, so that was basically some general comments I would like to make about the lattice model. All right, so now we are ready to look at the famous example of XSX Heisenberg spin chain. questions so far before I kind of move into it? Or maybe it actually become more clear when I talk about this explicit example of spin change. Okay, so I guess I can keep this diagram. All right, so we'll be looking at the explicit example of x spin half spin change, usually denoted by this spin level half spin change. So the Hilbert space describing the system is given by the tensor product. So we're still looking at a kind of periodic chain of n spins. It's given by tensor product of an individual Hilbert space tensor together. And we'll be interested in the spin observables. Such, and we make the periodic identification. Okay. So on each individual site, since it's two-dimensional, so we'll be representing the S alpha simply using Pauli matrices. Okay. So there are a few important observables. The first one is, of course, the Hamiltonian, which is describing the system. And that is simply given by n1, capital N, S alpha, n plus 1, and n plus 1 minus quarter. So basically, I think Yongquan was labeling those guys by J's yesterday, but that's fine. So, but what it actually does actually become more obvious when I write it in a different way. So right now, you are basically just looking at, well, like two neighboring spins. Basically, only the neighboring spins that talk to each other. But what it actually does is that if we can also define another important operator, which is the permutation operator, is given by, I could have some index on two different vector space. Two. If you think about how, well, this operator acting on a vector space, which I denoted, for example, P12 and act on A1 tensor product A2. Okay, so those are simply a two vectors in the site 1 and site 2, and this operator basically change their order into A2 cross A1. You can really explicitly write it out. Or basically explicitly act this with this operator. So, but if you compare the permutation operator with Hamiltonian, you realize that the Hamiltonian, on the other hand, can actually be written as -1. So basically, the Hamiltonian, what it actually does is simply just interchange the neighboring spin states. Okay, so and then you can do a pairwise. If you keep repeatedly acting on the spin chain, then what the Hamiltonian actually does is kind of you swapping and swapping again, then you propagate the spin along this periodic chain, and there can be more than one of them. So, and another important observables is, of course, the total spin of our systems. So, for example, total spin is simply sum over all the individual lattice size. Okay. And what's nice thing about it is that if you compute this commutator with the Hamiltonian, this thing equal to 0, but that simply reflects the fact that our system has symmetries on the action of SL2, or basically our Hamiltonian has a symmetry on the invariant on the SL2. Therefore, you can have this commutation relation. Basically, angular momentum, total angular momentum is actually conserved in total spin. Sorry, total spin is actually conserved in our system. Okay. So what's the problem we are trying to solve? Well, so we want to find the spectrum, the energy spectrum of this spin chain. Or in other words, want to find the spectrum of spin chain or the eigenvalues of the Hamiltonian, or in fact also the eigen vectors or the wave functions. Okay. So of course this will become a diagonalization problem of this matrix operators. But you can, as I was mentioning earlier, that this can be actually very difficult because typically, and we are dealing with is very much larger than 1. So to actually perform this diagonalization problem, we instead introduce our good old friend, the lax operator. So right now, even if you don't like lax operator, you can just view it as, okay, so there's another matrix which we can introduce. But now, compare with our earlier version in the classical mechanic case, now our lax operators actually depends on an additional complex parameter, lambda. So I'll explain this, all those indexes momentarily. So So basically, n here simply labeling each of the lattice side, and it acts on, so this bit acts on the Hilbert space sitting at the site n. But however, to each of those lattice sides, we attach to it something called an auxiliary vector space, or auxiliary Hilbert space. Space, which I denoted as VA. So now you should really imagine that we so lambda is some complex parameter. C is equal to something called a spectral parameter, and its significance will become very clear very soon. It's actually something like an eigenvalue associated with the Lax operator, capital L, over there. So it will actually become very clear when we define. Because when you think about a Lax operator, the next thing you should think about are really kind of the conserved and commuting charges in your system. So actually lambda will be related to the values of those conserved charges.
What does the index A indicate?
A is labeling the auxiliary space.
So how many dimensions?
2 dimensions. In our case, it will be 2 dimensions. It's the same good. It's the same dimension as the individual Hilbert space. So now, if you want that to an n-side spin chain, so I was going to say that. So on our original Hilbert space, which would be something like V1, V2, and Vn sticking here, Vn. Okay. But now we kind of have another guy attached to it. That's our auxiliary space, and they are labeled by lambda.
So in the first line, do you mean essentially H1 and H2 instead of V1, V2?
Sure. So I guess I could also call this HA. Okay. And each of those auxiliary space HA is associated with a spectral parameter lambda. Okay. So, well, right now you can just view this as some, in our case, will be 4-dimensional operators, but instead of acting on those lattice sides, but now rather it acts on a lattice side, but another kind of additional Hilbert space. And for each of those Hilbert space, HA, we can associate with a parameter, a complex parameter, lambda. But this turns out to be an extremely useful way to think about, to solving this problem. Hopefully, by the end of this lecture, it will become very clear this is useful. So So actually, we can also write another representation of the lax operator. Is that we can also write it in terms of permutation operator, which we introduced just now. So do a simple change of variables. So this notation would really mean 1n tensor product 1a, okay, and plus the permutation operator. So that's basically telling you that if lambda is equal to I over 2, that's actually nothing, the lax pair, sorry, lax operator reduced to our permutation operator. So this will actually become quite useful later as well when we kind of try to pick out what's the momentum and the energy of this entire spin chain system. Okay? So just like when we were talking about the classical integrable system and the classical lax operator, we are really interested in the commutation relation between those different lax operators. So to deduce their commutation relation, so to know commutation relation among lax operators. Okay. So, and to do so, we can consider another auxiliary space. So I guess I would call this HA1, HA2. So yeah, actually, so that's why I was introduced using B instead of H, just to save the notation. So I use B to label the auxiliary space. So, but now there are two of them. Okay, so basically I want to consider two lax operators associated with V1 and V2. So there will be two different spectral parameters. So basically, the operators will be acting on Hn tensor product V1 and V2. Since this guy acts on H1 tensor product V1 and this guy acts on tensor product Hn is V2. Okay? And there could be another, so we can interchange the order we are acting on those lattice sites by considering it the other way. And the punchline is really that when you consider two different ordering of those Lax operator acting on this vector space, this tensor vector space, you should realize that these two, the only difference is that they are only exchanged among the action, basically the action of those two operators should only differ by their exchange in the auxiliary space. All we are doing is exchange those additional auxiliary non-physical space and changing their label, if you want. So that's telling you that there should be operators on the auxiliary. Let me try to write some words. So the punchline is that these two, the two are kind of similar operators. So only exchanging the auxiliary spaces V1 tensor V2. So there should be this on V1 tensor V2 and operator. And in fact, this is a quantum mechanical analog of the R matrix, which I was telling you on Tuesday. Basically, it goes something like this. So this is sometimes of the R matrix, such that R A1 A2 lambda minus mu L n A lambda L n A A2 mu is actually equal to, if you, so it's basically telling you, well, okay, I draw a diagram, then that will be very clear. Let me just write down this one. I'll give this a name called a fundamental commutation relation 1. So I will call this FCR 1, because we'll be widely using it later. So what's the diagram for this representation? Well, for this relation? Well, so some of you may have seen this before. And this kind of diagram appears in all sorts of places in mathematical physics and higher physics. So basically, if we try to represent yeah, actually, let me just write down the y and then write down the diagram. It's actually all uniform this way. So actually, so let me define, let me write down, I should define what the R matrices are, actually. So the R matrices is simply, also, there's